Electrons are electric. Electrons are electric. That's why they're called electrons. What we've been taught is they orbit the atom with lots of space between, kind of like what this little animation here is going to show. And that's what we're seeing is the illusion that they give us, the best that we can detect them and visualize them. I'm saying that is what they actually are is like little thunderstorms going around the proton. This is slowed down. Remember, electrons they fire around an atom billions of times a second or millions of times a second. So it's fast. That's how slow this is. But I'm going to give you an idea how my theory, the good vibrations, says the electrons are electric. Gravity is electric. So this is what it's going to look like, more like this as that thunderstorm goes around. It's an illusion that it's orbiting. It's just flashing at different points, and it may be organized in a circular fashion, but it's not a particle. So here, let's say there's 4 quarks inside a proton, and that's how I'm going to show this. And it may be different. Maybe it's only 3, up, down, and sideways quark, but they change position is what happens. And when your electron hits that top quark there, energizes it, it's electromagnetism, electrostatic magnetism. It pulls the other 3 towards it. Then it moves to another one and pulls it towards M3. So an M3 to M3, and then the side one and the side left one to them, the other 3 are pulled to it, and it keeps doing that. That's how it holds itself together. They change billions of times a second. Those little thunderstorms are going off. And it'll get faster and faster. Here, this animation will to show you. It's an electric charge. It's just so quick. We see it as something orbiting the atom or the proton or the molecule, but that's not what it is. You know, the more protons you get, the more little thunderstorms you got going on at the same time, different sides, different locations. So that's what mine says it is. I want to move on now to showing you more of how I think gravity is electrical. Okay, as I've stated before, there's a reason they call an electron an electron. It's electric-tron. There's an electric property to the electron of every atom. So we're going to say this is a demonstration I've got set up. So we'll say this little ball bearing here and this little track is like a proton or even a quark of an atom. And over here I have a coil with the steel center. And over here I have a coil with the steel center. So I have 2 coils, and I'm going to use this battery to energize them. But I'm going to energize one, then the other, then back and forth. And they have a common ground, and they'll have a switch where I can switch from one coil to the other. You won't see all the wires. I'm going to zoom in on just the ball bearing and the coils here in the center when I do this. But the point is, the electric current, which my theory, the good vibrations, it says the ether is full of charge. It's the atoms and the quarks or the good vibrating particles that make up mass, and they require the charge from the surrounding ether to hold themselves together. It's electromagnetic. That's what an electron is, electromagnetic, electrostatic, if you will. What this is going to demonstrate is how quarks hold themselves together, or how the charge of the electron uses the neutrons to hold the protons together. And it's all electrostatic pull, pull, pull. There are no pushes, really. It's a pull, pull, pull. But it changes position. So once I show you how this works, and you see it working, then we'll go on to an animation to showing what I'm saying this steel ball, and these are. These will actually be like neutron balls, the same size as this, or the same part of an atom, or other quarks, but I'm just showing how the one will move, or how they'll hold themselves together, hold each other together inside the atom, the strong force. So I'll show you how this works, then we'll go on to a little animation and explain why I say this is how gravity works and how magnetism, energy, everything works off the same principle. The electromagnetic or electrostatic bond of atoms, the strong force, that is each atom's gravitational property. Gravity is electric, which causes the electron, which is what holds atoms together. So each atom's electron function, or each atom or molecule or whatever piece of mass you have, the combined electron functions are its gravitational property. It's all electric. So now we'll move on to demonstrating how this works. Okay, here's our two electromagnets on each side. I've got this ball bearing right in the center. I'm going to put it in the center. We've got a left coil and a right coil. And this is going to show kind of what an atom does, except this is going to show the ball moving when I energize one coil and then the other. If I put two in there, it just does the same thing with less motion because there's two balls in there. But I'm just wanting to show you this is what the electron is doing. It's an electrical pole of the particles that make up the quarks. They're trying to hold themselves together, but when each quark is pulled on by that little thunderstorm, electron, it pulls on the other three quarks and it pulls them towards it. But it happens so fast, each one firing one after the other in an order, in a pattern, that it just holds itself together, and we see it as something orbiting the atom. But it's not, it's electromagnetic. The universe is filled with dielectric charge. It's friction instigated, and it's incoherent. It just is there. And would you not agree that it takes mass to make light or radio waves or electromagnetic beams, if you will, to make those happen? It takes mass to make those happen. Light, radio waves, gamma waves, gamma rays, microwaves, ultraviolet, all those electromagnetic waves, it takes mass to cause those to happen, whether it's hydrogen or ferrite or whatever, any element. So for those to propagate through the dielectric of friction charge, friction instigated dielectric, the mass that's creating the light or the heat or the electromagnetic waves, that is what gives the dielectric coherency for light, electromagnetic waves to travel. They give the dielectric coherency as it goes. But when it's mass itself, it creates a stability for the dielectric to feed. It's a consumption. The mass consumes the dielectric to hold itself together. That's why the electron is called an electron. It's electric. So what I want to show here is that a magnet is basically two infantile or infant or juvenile Birkeland currents coming in from each side to feed this thing in one direction instead of all the way around like it would this same sphere if it was not magnetized. So those two infant Birkeland currents of dielectric, it's streaming the electrons. They are streaming into the magnet from both sides. Now, the reason the magnet, I say it's not just a 0-point coherency of dielectric, is because it should have the same effect on this plastic as it does on copper or aluminum or steel, but it does not. It does not have the same effect on all. I can move this plastic along the side here without touching the magnet. It does nothing. The magnet, the dielectric or infantile Birkeland currents go right through the plastic into the magnet. It does not care because it does not concede or contrive to the vortexing influx into the magnet. It just lets it pass through, or the electron functions of non-conductive items go right into the magnet through the piece. However, if it's a conductive metal, which means electric, like electron, electrically conductive, there's a different thing. This does not stick, but if I get next to it and move it, look at the magnet. It moves. I'm not touching it, but it moves. That's copper. Aluminum will do the same thing. Not nearly as powerful, Now, if I had brass or lead or other electrically conductive elements, they will do the same thing. They will interact with the Birkeland currents going into the magnet because they are electrically conductive. Now, steel is electrically conductive, but it has the electron functions of steel adhere directly to what the magnet's vortexing, streaming Birkeland currents do. It adheres exactly, and it follows suit. It says, well, I can do that, and I'll do it just like you do all the way through me, but temporarily. The point is, this doesn't stick, but it does try. That's why it moves the magnet. So that's the whole point. It's electric. And if I haven't shown yet, I will show what an electron is. It's an electric conduction into mass to hold it together, which is why it's called an electron. Okay, so we'll move on. Well, we'll move on to showing you more how I know why the magnet is too infantile, proportionately powerful, but infantile, dual, bilateral, bilinear Birkeland currents. They phase each other out at the middle of the magnet, or depending on the shape, size, and length, and what have you of the magnet, they cancel each other out so far into the mass, and this mass with this size, with magnets smaller of size, they cancel each other out as they touch. If the magnet is long enough, the steel or whatever magnetized mass, then they cancel out so far along when natural dielectric takes over. Natural gravity between the poles.